All right. Last time we talked about sections 8.4, and I asked you guys to work on what, like 51 to 76 or whatever. Let's start by taking questions from there, or previous homeworks is fine also. Max. 48. So it says a crate of negligible weight. What does that tell you right away? There's no gravity going on, right? Okay. Is being pulled up a ramp at an angle of elevation of 53 degrees with a force of 105 degrees. What is that information telling you? It's the magnitude and direction for some vector. I'm going to call that vector P for pull. It says the ramp is 15 feet long and 8 feet tall. What is that telling us? That's the component form for the ramp. What is the amount of force being directed up the ramp? So what are we looking for then? The magnitude of the projection of the pull onto the ramp is what we're searching for. Everybody okay with the setup there? Okay. Noted here right away that the ramp vector, not a unit vector, obviously. We can look at it and see that. That tells me that I got to do this the long way. So I'm going to use the full projection formula for my vector. Cool. In order to do anything with this, we got to really start by putting P into component form. So let's do that next. So far, so good. All right. And at this point, it's basically just calculator time. We've done the setup. So 105 cosine 53, 105 sine 53. So let's go ahead and do that fraction so we can do the scalar multiplication. So it's this times 15 plus this times 8 divided by 15 squared plus 8 squared. So that's the scalar that I'm multiplying in, is this 5.6 number. So when I do my scalar multiplication and then take the magnitude of it, I'm going to do that all at once. So it's going to be this number times 15. And then because I'm taking the magnitude, I'm going to square it, plus this number times 8. And again, because now we're doing the magnitude, we're going to square it. And I notice that's all under the square root. So I get 95/22. Cool. All done. Oh, brother, who asked about this? Who was Max? That was it. Max, is that? Okay. Aaron?
Can you just explain the calculator part again? Like, can you just go through that again?
I mean, it doesn't matter how you're really doing it on the calculator. I tried to do it like without having to, just minimally doing this, but I did the dot product. So I do like cosine 50, or 105 cosine 53 times 15 plus 105 sine 53 times 8 over 15 squared plus 8 squared. And I still have to multiply that by 15, 8, the vector, right? So when I do that, I have like 105 cosine 53 times 15 squared plus 105 sine 53 times 8 times 15 all over 15 squared plus 8. You know, you're just multiplying it. You just, I don't know, like however you want to type it in the calculator, whether you do it in like a bunch of steps or one step, it doesn't really matter. You know what I mean?
Yeah.
Like just use the fraction command, but I'm just using like the definition of the dot product and stuff and the definition of magnitude. Taylor?
Where did the 15 come in?
What?
Where did the 15 come in? On the top, the second part of it? Why is there 15 on that?
Because that's just the first component of my new vector when I do the scalar multiplication. So I'm taking this.
Oh, we're doing that.
It's the next order in the order of operations, right? I got to do the scalar multiplication before I take the magnitude. You know what I mean? Just how you want to type that in your calculator, whether you want to do like all the algebra by hand or do like...
But why is the 15 in both parts and the 8 is only in one?
This number
Yeah.
gets the 15 multiplies to both parts of it.
So did the 8 multiply?
It would if I bothered to write down the other part of the fraction. I was just kind of like talking and writing for Aaron. Is that however you want to do it, whether I made this fraction a number and then multiplied it to each piece on my calculator and then did the magnitude all at the same time because didn't make sense to me to like do the scalar multiplication and then do the magnitude after it when it's like I can just type it all in at once. You know what I mean?
Did you give us the equations from the...
I'd give you the projection formula. Dot products, magnitudes, converting between the different forms, vector addition, that stuff's on you. Eddie.
Wouldn't the 15 squared plus 8 squared be in that square root?
Well, it would, but it's also squared.
Oh.
So they would just kind of cancel each other out. And I didn't bother to, I just did it in my head or whatever. But you could certainly put it there and then cross it, it's fine. Or type in your calculator, the calculator will handle it,
But for the final magnitude, like for the final answer, in order to get 95.2, do that original one have to be in the square root too?
What do you mean the original one?
The magnitude for the final 2 points, the component form.
Yeah. Like once I did this and got my 2 points or my component form, then it's like, yeah.
So why does that one?
Because this isn't magnitude squared.
Oh, okay.
It doesn't have a squared there at the end. It's just the magnitude. Yeah, no problem. Jake.
So, HTPC number?
39. Uh, 39 asks for, show that two vectors are orthogonal. Orthogonal just means that they intersect at a right angle, or the angle between them is 90 degrees. So to do that, all we need to do is do their dot product and show that you get 0 from that. And we're done. That's it. If the dot product's 0, the vectors are orthogonal. We had a theorem or something in our notes, but that's all I'm using to do that. Jose.
You can see number 7.
Yeah, sure. So it has two lines, and we're wanting to find the intersection of these. This is probably the hardest thing that we've asked you guys to do so far. Okay, so the trick here is I'm going to turn R1 into a single vector by just doing the vector operations between the vector 0, 8 and then the vector 1, 7 times s. And the same thing for R2. And then if these two lines are going to intersect, the vectors R1 and R2 need to be equal. So I'm just going to set these two vectors equal to each other then. Okay with that? And for that, those two vectors to be equal, the x components have to be equal, and the y components have to be equal simultaneously, like at the same time. So basically this turns into a system of two equations. So I'm going to solve this system then. So I'm going to go ahead and put it in kind of that standard linear form. So the first equation, I'm going to subtract 6t over. The second equation, I'm going to subtract 4t over, and then subtract 8 over. That's going to give me a two-variable system. I'm going to solve that system with my calculator using a matrix. So I'll press second and then the x to the -1 button to open the matrix menu. I'll go over to the edit tab. I'm going to edit matrix A. This system has two rows and then a column for s's, a column for t's, and a column for solutions. So it's a 2x3 matrix. And then I'm just going to type in the coefficients into my matrix exactly as they appear in my system. Once I've typed things into my matrix, I'm going to exit back to the home screen. Then I'll go back into the matrix menu. I'll move over to the Math tab, scroll all the way to the bottom and find the RREF command. And I'm going to do that RREF command on my matrix A. Okay, so let's write that down, what we just did here. Oops. What was it, 3 and 2.5? -3 and -2.5. Okay. So this matrix that I got from my calculator tells me that S is -3 and T is -2.5. And to get the point of intersection, or the point vector really of intersection, I could take either the S or the T. I'm going to choose to take the S because there's no decimal. It makes the arithmetic a little bit nicer. And plug that into the vector line equation at the beginning that also had the S in it. That was R1. So when I do that, I get -3, -13. So that's the point of intersection, or point vector of intersection. Is that okay, Josie? You want to talk through that one more time? I went kind of fast.
I'm just confused on the adding. for the last part?
This last step,
If you multiply -3 to just the 1, 7.
yeah, it's scalar multiplication. So I do the scalar multiplication first, and then I add the result.
And then you just add the cross.
Yep, just we're adding two vectors.
Okay.
So just following the vector order of operations, we do the scalar multiplication first, vector addition second. So I do 0 plus -3. That gives me the -3. And then I give positive 8 plus -21. That gives the -13.
Okay.
Yeah, no problem. Again, the place that students will frequently get confused is stopping and saying, oh, -3, -2.5 is the point of intersection. It's like, oh, no, no, no. Those are the parameters that give us the point of intersection. We still need to find that point of intersection, though. No problem. Jake?
I suppose with the question, you have when one of the vectors is a unit vector, that's when you don't have to divide it.
So in general, if the magnitude of u is 1, then the magnitude of the projection of v onto u is just the absolute value of the dot product of v and u. Yes, sir?
Was there a notebook found in here, this class?
Nobody turned one in, but if you want to take a look at where you were sitting to see if you left something, you're welcome to do so. Yeah, no problem. I didn't notice anything, but doesn't mean that I wasn't looking either, so.
Thank you.
No problem. So yeah, Jacob, this is the situation that you're asking about, right?
Yeah.
So if u is the unit vector, then the projection of v onto u is just the absolute value of the dot product of u and v. Or v and u, it doesn't matter, the order of dot product. And that's a nice shortcut for a lot of those projection story problems. I think most of them you can use that shortcut on. There's just like one or two that you have to be careful about, but. Josie.
Page number 69, please.
Sure. So it says to find a possible vector line equation that goes through these points. That's not exactly the directions, but like it's whatever. So there's two things that I need to write my vector line equation. I need a point vector. So the obvious 2 point vectors to pick would be, the ones that correspond to the points that I'm given. So it doesn't matter there. And then we need a direction vector, which I know is equivalent to the slope. So I'll calculate the slope first. So that gives me -1/5. So again, the two obvious slope vector or direction vectors then I would use are either 5, -1 or -5, 1. It doesn't matter where the negative sign is. So for example, then my vector line equation would be, could be this. I think there's 4 possible answers that you could kind of combine these things, but you don't have to list all 5. 1 is fine.
Okay.
Sure. And again, I wrote this in IB component form, and that's because that's what the directions asked for. They wanted linear combination of form or whatever. There's a little bit of extra cleanup after you do this, but I would always initially write it in IB component form and then shuffle things around if I needed to from there. But yeah, but that's pretty easy, right? Just knowing what to do is the hard part.
Yeah, no,
But
I
actually,
wanted to start.
Yeah, doing it is like, oh, that's it?
Yeah.
That's it. But it's just like knowing what to do kind of thing. Unlike some like terrible solving problem where it's like, okay, I know what to do, but actually doing it's the hard part. Here the doing is easy. The what to do is the hard part, Tay.
So last class we went over number 50 on the homework.
Okay,
And I'm just curious.
sure.
When there's 3 different vectors, how do we like determine that there's 3 different ones and like what part goes to each? And then which ones are being added together and projected onto the other one?
Okay, so the forces are the ones that are being projected. So I read a weight, that's a force. The crate has a weight, that means there's gravity interacting here. So that's one vector right away. Just by the first sentence where it says the crate weighing 80, I stop right there. That's gravity, that's a vector, boom. Is being pulled, okay, pulling is a vector. So that's a second vector. And it tells me that it's going up the ramp at an angle of elevation of 29 degrees with a force of 130 pounds. So that's the magnitude and direction for the pull vector. And it says the ramp itself has an angle of elevation of 22 degrees. Okay, that's my third vector. That's the ramp. There's no force associated with a ramp because a ramp is just like a thing, right? It's not like it's not a force. It doesn't interact with anything. It just sits there and doesn't move. So that's how I know that I'm projecting the other two onto the ramp. Also, if I read the last sentence, it says, what is the amount of force being directed up the ramp? Since it's being directed onto the ramp, we should be projecting onto the ramp. Does that help just kind of talking through as I read it, how I'm decoding that?
Yeah. And then, so for this one, we just had the ramp's magnitude be 1.
Yep.
If it were to say that it was like, like the one there, it's like 15 feet like long, like 8 feet tall, like that's like component form.
Yep, that would be
so
the
find the magnitude from that.
You wouldn't. I don't know. You could. You don't really need to find the magnitude directly, but like you can type it into your calculator and not actually like figure out what the magnitude number is for that.
Okay.
But you should be able to look at it and be like, yeah, it ain't no unit vector.
Okay.
That's all you really care about. You know what I mean?
Mm-hmm.
Is that?
Yeah.
That's enough?
Yeah, that's all I was just trying to figure out, how we determine what parts go where.
Sure. Yeah. Okay. Eddie.
Could you go over 16?
16 says we got some points. We got A, we got B, we got C, and we got D. And they want us to do BA minus 3CD. So first thing I'd want to do is I'd want to resolve these points into component form vectors. So I'm going to use the head minus tail rule. So A is the head. So I'm going to do 3 minus 5. And then I'm going to do 1 minus a negative 4. And then we'll do the same thing for CD. So D is the head. So I'm going to do negative 1 minus a negative 2. And then I'm going to do 6 minus 9. Next thing in the order of operations I do is the scalar multiplication. So that negative 3 is going to get multiplied through to each component. Notice that I took the whole negative there, so I really kind of thought about this as plus a negative. I like to do that rather than doing subtraction because I always feel like I'm going to forget to subtract the second component or something. And then I just add these puppies up. Oops, 14. And I'm all done. Oops, negative 5. That's it. Does that feel okay? So again, like operations are easy to do. It's just kind of remembering how to do these operations, right? Is that Elvis, is that hand? Nope, you're just chilling? Cool. Jake, you had a hand, did you? Oh, yeah, right on, brother.
So for number 50, I just wait that something like that. Are you always going to be projecting the unit vector onto the
Other way around.
Or other way around?
Yeah, I mean, the last sentence tells you what you're projecting onto, right? Because it says, what is the amount of force being directed up the ramp? So you're projecting the forces onto the ramp, just from the context of the question. But yeah, I mean, for questions like this, it makes no sense to project a ramp onto a force. A ramp isn't a force, it's just a thing. It sits there, doesn't do anything, right? It's basically asking, okay, you're doing all this pulling, how much are you actually going in the direction that you're supposed to be pulling? Like actually working to get the thing up the stupid ramp. Ideally, you'd like 100% of it. You'd like to pull in the same angle as the ramp so that all your pulling is going to use, but that's not always how life works. You know what I mean? Okay. Let's stop here question-wise. We can always come back and ask some more later on. That's good. What we'll do now, we're going to go through and do sections 8.5 and 8.6 here right quick. And then whatever time we have remaining is going to be filled with that homework quiz that you guys all knew was coming. Okay. So we're going to start in section 8.5, talking about the three-dimensional coordinate system. If my stupid machine wants to respond. There we go. Okay. So this is what the 3D coordinate system looks like. The line that's dashed there, you need to imagine in 3 dimensions. So the dashed line in the lower left-hand quadrant, you need to imagine like coming out of the board towards you. And the dashed line in the upper right-hand quadrant, you have to imagine going into the board, like into Miss Garcia's room. So take a moment, look with your 3-dimensional mind and kind of picture that. It's a little bit tough because we're putting a 3-dimensional object on a 2-dimensional sheet of paper. But you have to just use a little bit of imagination. You should be able to see it. So when we name these 3 axes, these are the x, y, and z axes. This is the part that all students hate because this is your x, this is your y, and this is your z. And all students at this point groan and go, oh, that's not the order I would want to name these things. But that's what we've chosen to do as mathematicians. This end is the positive end of the x. That's the negative end. Positive end of the y. Negative end. Positive end of z. Negative end of z. So first thing we're going to talk about now is going to be plotting points in this 3-dimensional system. Let's say we want to plot the point 3, 2, 5. And just FYI, when we name these points in 3 dimensions, we always list them X, Y, Z, alphabetical order. Probably goes without being said, but let's say it and be specific, right? Okay. So when we graph things in 2 dimensions, it was very easy because we're just taking a 2-dimensional thing, putting on a 2-dimensional sheet of paper. Nothing confusing about that. Here we have a 3-dimensional thing that we're putting onto a 2-dimensional sheet of paper, which means we're going to have to kind of do a projection thing here, which can be a little bit confusing. So let's kind of let's do this example and be really specific, and we'll go nice and slow through it. Okay? So the first thing I'm going to do is I'm going to start by putting 3 tick marks on the positive end of the y-axis, 2 tick marks on the positive end, 3 on the x, 2 on the y, and then 5 on the z. Everybody's okay there? So to plot this point, what I'm essentially going to do now is I'm going to build a box. So this is what I'm going to do. I'm going to start by building the base of the box, and I'm going to use this side of the x-axis is one side of my box. This side of the y-axis is another. And now I'm just going to kind of make a parallelogram here. So this point now at the corner is basically the point 3, 2, 0. Because we've gone nowhere up and down. We've just plotted a point in the xy plane. Does everybody feel okay doing that piece? Okay. What I'm going to do now is I'm going to build the sides of my box. Boy, that didn't, let me make that a little straighter. Yuck. It's hard without a ruler. I would love a ruler. I don't know. I don't think that's any better. Whatever, I'm a failure. Next thing I'm going to do is I'm going to draw the sides of my box. So I'm going to start by drawing up in the z direction. So these two, oh my goodness. Go up like that. And then I'm going to go down to this corner here. And I'm going to draw my vertical like the same height or the same length as those other two sides that I just drew. And I'm going to do the same thing here. Everybody's okay with that? So that finishes my box off. This point here is that point 3, 2, 5 now. So if we take a look in 3 dimensions, what is this box really representing? Well, this was our 2-dimensional version of the point, right? We're in that same XY plane. And what we've done now is we've just lifted that entire XY plane 5 units in the Z direction. Basically just projected that up 1 dimension, right? We took a 2-dimensional point and then lifted it into 3 dimensions, basically. Every day I forget about this. Every day it bothers me. Okay. Should we do another? Again, not terribly difficult what we just did, but like takes a little getting used to. Take some practice. Let's do this time, instead of a point, let's do a vector. So just to remind you guys, in 2 dimensions, when we graphed the component form vector, what we did is we plotted the point and then just connected the origin to our point and drew the arrow, right? Does that sound familiar? We're going to do the same thing here. So I'm going to start just by trying to plot the point to -3, 4, and then I'll connect the origin to that point. So again, I'll label my X, Y, and Z axis. I'll start by drawing some tick marks. So 2 on the X, 3 on the Y. Notice I'm going in the negative direction on the Y. And then 4 on the Z. Okay. I'm going to now draw the bottom of my box. So there's the point 2, -3, 0. And all we need to do is lift this point into 3 dimensions. So I'll just draw the sides of my box now. Again, I'm just trying to draw these sides in front to be the same length as the sides in the back that I drew. I think this one turned out a little bit nicer. So there's the point 2, -3, 4. But if we want the vector, really we're talking about this guy right here. All right, we got to make sure we draw from the origin to that point. That is our component form vector. Is that feeling a little better after doing another example? Again, those of us that are like handwriting impaired, this becomes kind of a challenge just because you have bad penmanship and like it's hard to be neat. If you at least have bad penmanship, but you can summon your good penmanship when you need it, you can be okay. Those of you that it's like everything I draw looks like a scribble farm, I'm sorry, it's going to be tough. You know what I mean? But use some different colors, use some dashed lines if you need to, do something to help differentiate yourself what you're looking at. I like colors. I think it makes it a heck of a lot easier to see what's going on if I use different colors to do some stuff like I've done here. Be creative. I'm never going to complain about it. Cool? Okay. So in 2 dimensions, if we have a 2-dimensional XY space, 2 things that you can do right away. You can define a distance between 2 points. So in 2-dimensional space, that distance formula was x1 minus x2 squared plus y1 minus y2 squared. In 3-dimensional space, we just add in a z1 minus z2 squared, which I hope would be exactly what you'd be looking for, right? That's about as good as you could hope to get. Translating a 2-dimensional formula to a 3-dimensional formula is like, yeah, there's just like an extra little part for the 3-dimensional part in there, but it's like the same form and function as the 2-dimensional. That's pretty nice. In addition, in 2-dimensional space, if you're given 2 points, you could find the midpoint between those 2 points. So the x-coordinate is just going to be the average of the x-coordinates. And the y-coordinate would just be the average of the y-coordinates. So in 3 dimensions, we just have another component for the average of the z-coordinates. No big deal, right? That's as good as you could have hoped for, going from 2-dimensional stuff to 3-dimensional stuff, where essentially it's the exact same formula, just have a little bit of extra for the third component. Cool? Okay. In section 8.6, we talk about 3D vectors. And really all we're doing in section 3.6 is translating the forms and formulas that we had for 2 dimensions into 3 dimensions. So let's see. So some of our vector forms, right? We had component form. So in 2 dimensions, we wrote the component form like A comma B. In 3 dimensions, we still use the wedge brackets. We just add a third component in there. And if we were to draw that, that's the vector that goes from the origin to the point ABC, right? Exact same definition as 2 dimensions, just, you know, like extended to 3 dimensions. So we have the IB component form. In 2 dimensions, that was the vector AB, the column vector AB. In 3 dimensions, it's just the column vector ABC. Mr. Kulik, you're blowing my gourd right now. Hey, guy, hang on to your hat. We had the linear combination form. So in 2 dimensions, that was AI plus BJ. Well, in 3 dimensions, we have a third component, so we'll have plus CK. So remember these vectors I and J were called the standard unit vectors in 2 dimensions. They're still called the standard unit vectors here in 3 dimensions. But I, instead of being 1, 0, is 1, 0, 0. J, instead of being 0, 1, is 0, 1, 0. And the new vector K is just 0, 0, 1. Methinks you probably would have guessed that had I given you the opportunity to. And it gives me the opportunity to say the word methinks, which is not something you hear every day in English, which I was pretty excited to sound like a medieval bard there. So to go from points to component form, remember in 2 dimensions, we just did the head minus tail rule. In 3 dimensions, we still use the head minus tail rule. Let's see, let's do U. How do I want to say this? I'll just say X. Right, like nothing to it. Exact same formulas, 2 dimensions, just had a third component to it or whatever. So this is all very good, right? This is what we hoped for. Agreed? So remember, in 2 dimensions, if I had the vector AB, its magnitude was the square root of A squared plus B squared. In 3 dimensions, the magnitude is just the square root of A squared plus B squared plus C squared. Mr. Kulik, so easy. So what? Yeah, exactly, so what? So let's just say from here on, we have the unit or the component form vectors U and V. So if I wanted to add the two vectors, guess what we do? We add them the same way we did before, just adding the components together, just instead of having two components to add. Now we have three components to add. Oh my gosh. Subtraction, guess what? Again, same thing. Scalar multiplication, guess what? Again, same thing. Oh my goodness, Mr. Kulik, does this just stay so easy? Well, so far. Dot product, does this change? No way, Jose. Woo! Well, there's gotta be some kind of catch, Mr. Kulik. Do all the dot product properties hold from two dimensions? Yes, they do. Well, okay. Well, that's great. So no problems there. Well, what's the catch? What's going to make three dimensions so much harder? What haven't I mentioned here? We talk about it all the time in two dimensions. Direction. We haven't talked about direction yet, have we? In two dimensions, how do we describe direction most often? With an angle, right? Everybody agree? What the heck does an angle mean in three dimensions? I guess like the corollary object be like a sphere, which is not how we're going to do things. So we'll talk about how we're going to describe direction of vectors in three dimensions a little bit later, but we're going to leave that part off for right now. So that, just make a note to yourself that we're going to circle back to that idea, but it's not trivial. But done with describing angles in terms of degrees, that goes out the window when you start having 3 and 4 and 5 dimensional objects. That's no longer really helpful. Okay? Cool. Let's do just like a quick little numeric example, and then we'll get this show on the road. So let's say we have the vector u, the component form vector -2, 4, 7, and vector v, which is the linear combination form vector, 7i minus 6j minus 9k. And I just want to do 2u plus v. Well, the first thing I would do is I would just convert this linear combination form vector into component form, which works just like it did in two dimensions. Piece of cake. Okay. When I do vector operations, scalar multiplication happens before vector addition or subtraction. So 2 times u becomes -4, 8, 14. And then when I add the vectors together, -4 plus 7 is 3, 8 plus -6 is 2, and 14 plus -9 is 5. And this should feel exactly like the things we did in two dimensions, except there's like a third component. Big whoop, though. Everybody's okay with that? These two sections were the calm before the storm, because the last section in particular is the most challenging one. It's the one that you should be dreading. Okay, but that's enough for today. At this point now, you guys should be able to do up to 94 in the problem set. I know, it's exciting, isn't it? We'll see if we can find you some time this week to get some stuff done also. Okay?
I honestly got a picture of
I-
definitely Thursday.
It feels like that's probable.
So why don't you just give us like a work day then, or what do you want to lecture?
Depends on where we're at with everything else. Yes, Eddie?
Do you have a calculator tomorrow?
Sure. All right, folks. Let's get ready for this homework quiz.
No, you can't kill that.
Thank you.
Yes, let me finish passing these out and I'll get you one, okay? I do too. Let me finish passing these out.
It's like a 7 on it. It'll get drawn. So it's like, you know what I'm saying?
Yeah.
So I was doing the math in my head about how many I need to get.
As with anything in life, you just do the best you can in this moment. You did the best you can in the moment. There's nothing to feel bad about. And you learn from what you were able to do or not do, and you try to do a little bit better next time. And if you just keep getting a little bit better every day, before you know it, you get real good at something. And you're like, Mr. Kulik, that sounds like a load of crap, but I'm telling you, that's the way the world kind of works. It's just incremental progress. Nobody gets good at something all at once in a day. You know, don't be fooled. Even the people that appear to be seem like they get really good at something instantaneously have not done it instantaneously. They've been working their tail off, and just different people need different amounts of work in their tail off. Hi. I think they're honking at me. That was a joke, clearly. Oh, why would they be honking at me? They don't even know I'm here. Okay, I'll stop talking now. As a reminder, we finish at 1:20, so you guys have 25 minutes or so, and I owe some people some calculators that I almost forgot about. Jabberjaw on not bring you a calculator after I told you I would. Oh my goodness. Okay. All right. Now that everybody's got their stuff, take a moment and you're going to need this formula for the last problem. So take a moment and write that bad mama jamma down somewhere near that last problem for yourself, because I'm going to turn off the projector so I can do a little bit of my own business while you guys are doing this. But I think I owe you guys that. The other vector operations I'd expect that you guys have aren't able to do, but this one I'll give to you because, yes, sir. Oh, yeah. Woo! Close call. Close call. We got it though, don't worry. But one of you guys was going to correct me. Elvis won the correction race. This is what I get for trying to talk and do something at the same time.